Assalamualaikum, good morning and greetings to everyone. My name is Mohammad Hanis bin Mohammad Sharudin, and today I will present my Geometric Research Innovation Competition of 2026 entitled Geometric Differences Assessment between Slam-based Handheld 3D Scanner and UAV Photogrammetry for Transmission Line Infrastructure Area 3D Modeling. Okay, before we proceed this presentation, let me briefly explain about the background of this study. First, transmission line inspection requires accurate and efficient 3D data to support infrastructure monitoring and modeling. Traditionally, different data acquisition methods can be used to capture infrastructure information, but in this study, two approaches were compared, which are SLAM-based 3D scanning and UAV photogrammetry. Second, UAV provides wider coverage from an aerial perspective. Meanwhile, SLAM from the handheld 3D scanner provides flexible and faster ground-based data collection. However, because of both data methods capture the environment from different perspectives, differences may occur in terms of point distribution, geometry representation, and spatial coverage. Therefore, the study focused on evaluating the geometry differences between both datasets. The aim of this research is to evaluate the geometric error of handheld SLAM-based 3D scanner compared to UAV photogrammetry point cloud in transmission line mapping application. In order to achieve this aim, there are two main objectives of this research. The first objective is to generate 3D point cloud of transmission line infrastructure area using SLAM-based handheld 3D scanner and UAV photogrammetry. The second objective is to assess the geometric differences of 3D point cloud generated using SLAM-based handheld 3D scanner against UAV photogrammetry. For the methodology of this research, it consists of four main phases. The first phase is project planning, where site reconnaissance, planning, and preparation activities were conducted. The second phase is data acquisition, where both ground-based SLAM scanning and aerial photogrammetry data were collected. The third phase involved data processing to generate usable 3D point cloud datasets. And lastly, the fourth phase focused on analyze and evaluate the geometric differences between both datasets. Now, we will go through the methodology part regarding to the phase by phase. And the first phase is project planning. Basically, before data collection was performed, project planning was conducted to ensure the workflow was properly prepared. The activities included in project planning is site reconnaissance, ground control point marking, and preparation for both SLAM scanning and UAV photogrammetry. These steps were important to ensure that both datasets could be properly processed, then to be compared. The second phase is data acquisition. For data acquisition, two different methods were applied. The first method used a SLAM-based handheld 3D scanner to collect ground-based point cloud data. The second method used UAV photogrammetry to capture aerial image, which were later processed to be a 3D point cloud model. Both datasets represent the same transmission line area, but from different acquisition perspectives. The third phase is data processing. For data processing, different software were used based on the type of dataset. For the SLAM dataset, it was processed using Lixel Studio software, which involved point cloud processing and preparation. Meanwhile, for UAV photogrammetry image, it was processed using Argisoft Metashape in order to generate the 3D point cloud model. After this processing phase, both datasets were prepared for further geometric comparison. Next, we move to the last phase, which is result and analysis. For the analysis, it was conducted using Cloud Compare software. There are three main assessments were performed. The first is M3C2 analysis. It is to evaluate geometric differences between both datasets. And the second is cable diameter comparison, because for the cable, direct comparison using M3C2 was not suitable due to the different acquisition periods. And lastly is completeness assessment. It is to evaluate the similarity of spatial coverage and point cloud distribution. Here are the result of 3D point cloud that was generated using two different softwares. For 3D point cloud of SLAM, it is using Lixel Studio software. As you can see, the point cloud was more dense compared to the UAV one. Here are the analysis results for M3C2 analysis. For the M3C2 analysis, different objects showed a different level of geometric agreement. The results show that pylon and ground surfaces produce smaller differences because these objects have more stable and regular geometry. We took an example like pylon A. it recorded a mean difference only of 0.0014 meters, while ground recorded 0.004 meters. Meanwhile, oil pump showed a larger variation due to its complex structure, including irregular leaf branches and different viewing perspectives from both methods. Next, for the second analysis that was performed in this research is cable diameter comparison. For cable assessment, diameter comparison was used instead of M3C2 analysis. This is because the datasets were collected at different periods of time. So, the environmental conditions like the temperature will affect the cable position and the cable stack. Based on the graph that I have provided in this slide, we can see that the blue bar represents the SLAM data and the orange bar is represent for the UAV data. So what I can say is there is the big difference in between both measurements, where the RMSE represents the overall variation between the extracted cable diameter values. Hence, the difference observed is mainly related to the acquisition condition and the cable behavior itself. Completeness assessment was performed to evaluate how well both datasets cover the same spatial area. Based on the result that was shown in this slide, there is the different objects have different matching percentage. For an example, oil pump only recorded 27.3% matching cells, which indicates large differences in representation due to its complex structure. Meanwhile, rigid structures such as pylons show better matching because their geometry is more stable. Hence, the difference indicate that both systems capture and represent the environment differently based on their acquisition method. As a conclusion, both land-based handheld scanning and UAV photogrammetry are capable of representing transmission line infrastructure. However, differences were observed due to differences in acquisition perspective, point cloud distribution, and spatial coverage. So the results show that SLAM has potential for infrastructure 3D modeling, especially when flexible and efficient ground-based data collection is required. Instead of replacing UAV photogrammetry, SLAM can be considered as a complementary approach depending on the project requirements. Last but not least, there are a few recommendations that I will recommend and can be considered for future improvement. First, both datasets should ideally be collected within a similar period to reduce the influence of environmental changes, especially for dynamic objects such as cable. Second, more study areas and different infrastructure conditions can be tested to improve the reliability of the findings. And lastly, for future studies can explore the integration between SLAM and UAV datasets to combine the advantages of both methods. And that is all from my presentation, and thank you for your attention.